So in this problem, we want to determine this hydrostatic force on the following triangular plate that is submerged in water as shown. So we are also given the density of water, which is 1,000 kilograms per meter cubed. And we are also given the gravitational acceleration, 9.81 meters per second squared. So the first thing that you want to do in order to find hydrostatic force is, let's just think about what the formula for hydrostatic force is going to be. So let me go ahead and just put this maybe in a different color. Let me zoom in. So what we want to find, okay, this is what we want. We want the force, and we know that the force is going to be given by the pressure times the area. Okay, so there are two different pieces that we need to figure out. We need to figure out the pressure that is at this particular triangular plate, and also the area. So first, let's go ahead and find the pressure. So first, find pressure. Now, because the pressure itself is different at different points, if I were to get one little slit right here, well, the pressure here is going to be very different than maybe the pressure down here, because you know that if you go further down into the water, the pressures that you feel is going to be much higher. So you know that the pressure is going to be very different at different points on this plate. So we do not know that pressure is constant. It's definitely not constant. So we need to figure out what the pressure at one particular point is going to be. So let's say we take this little rectangular piece of this particular plate. We're taking it. And let's just call this a difference between one piece to another piece. And we're making it really, really thin. So this is going to be just delta x. Okay. And what we're going to do is that we're going to say that the distance from the surface down to this little rectangular sheet is going to be just xi. Okay. So what would the pressure be? So the pressure is given to you as rho g times d. Okay. So we know what rho is. Rho in this case is going to be 1,000. Okay. Gravitational acceleration is just 9.81, and then the distance is in this case is going to be xi, which is going to give me 9,810 times xi. So that's going to be the pressure acted upon this particular little slit. Okay, so that's the pressure at any given point. Okay, and notice that we're starting at the surface all the way to 4 meters down. Okay, so now that we found the pressure, now let's find the area. Okay, now find area. Okay, so if we look at the area of the strip, okay, so we're going to write here area of strip, because that's what we are looking at. We know that that's just going to be the length times the width. Okay, so we know that the length of this thing, well, we can call anything the length, but we know that this guy is just going to be delta x. So we're really looking for this width part or length, whatever you want to call it. Let me just call it length, because we know this width part is going to be delta x. Okay, because that's going to be this guy. This guy's going to be delta x. That's my width. And how long this is, well, then we really don't know how long this guy is, because we know that the length of this thing is going to be different in different positions of this triangle, because if I put it over here, then that's going to be very different length. Okay, so what would that be? So one thing that you can do, you can use similar triangles. So if I were to have this triangular plate, okay, and I were to maybe divide it by half, let's just say we do that, okay, and we're looking for this slit. Okay, there's my slit, so I basically drew it in green. We know this is delta x. We know how far this thing is. This thing is just 4 meters. Okay, this guy over here, from there to there, is how much? 6 meters. Okay, all right. And now all we need to figure out is what exactly this length is going to be. So if I were to divide it by half, let's just say we divide it by half. Okay. Well, if I divide it by half, half of 6 is going to be 3. So here's 3 meters. Half of 4 is going to be, well, not half of 4. It's just going to be still 4, because we're dividing the height. So it's going to be 4. And then here is going to be my little slit. Okay, we're going to call that A. Okay, so if this guy is 4 meters, and we said that the distance between the slit to the surface is xi, this bottom part is going to be 4 minus xi. Because we said that from here to here is going to be xi. That's what we said from the very beginning, right over here, xi. Okay, so the other part is going to be 4 minus xi. So by similar triangles, we know that this is going to be 3 over 4 is going to be equal to A over 4 minus xi. Move that over, A equals 3/4 times 4 minus xi. Okay. Now notice that this is only half of this triangle. We only know this guy. Now we want the whole thing. Okay, so this is A. This thing is also A. So all I got to do is just multiply this by 2. So I know that A equals 3/4 4 minus xi. So that means 2A is going to be basically multiplying this whole thing by 2. Okay? And then what you're going to have is 3/2 4 minus xi. Okay? Now, alternatively, you didn't need to divide the triangle into halves. You could have just used similar triangles straight up off the bat, and you would have still gotten exactly the same thing. Okay? So what is going to be our area? So our area is going to be the length, which we just figured out, which is going to be 3/2 4 minus xi times our width, which in this case was delta x. Okay, if you called it differently, it would have given you the same thing. Okay, so now we basically have what we need. We found our pressure and we found our area. So now let's find the force. Okay, now find force. Okay, so the force in this case, the force of this one slit, and I'm going to call it I because there's going to be many different slits. Let's just call it the ith slit. It's going to be equal to PI times AI. Okay, so I'm going to have our pressure, which in this case was 9810 times XI. That's my pressure. And then times A, which in this case is 3/2 4 minus xi times delta x. Okay. So if we have this, okay, this is going to be the force. Now, if I wanted to figure out the total force of every single particular strip that we get, right, the total force is just going to be equal to the limit as n goes to infinity of the sum of all of these different types of all of these strips of 9810 xi times 3/2 4 minus xi times delta x. Because basically we're summing n of these little strips. We're taking the limit, making them really, 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 really small. That's what this means, right? Of what? Of this pressure times area. Okay, so this we know from calculus that this is just going to give me the integral from 0 to 4, because we know that we are starting from the surface here at 0 all the way to 4. Okay, from 0 to 4 of what? So now it's going to be of 9810 x times 3/2 4 minus x. And then this delta x turns into dx. Okay, so let me go ahead and multiply a couple things out. I'm going to have, let me take out this guy and this guy. Okay, so what that's going to give me is going to give me 14,715 integral from 0 to 4. And then let me distribute this x. I'm going to have 4x minus x squared. So I got this guy, plug it in here, and then this guy, I just put it outside. dx. Okay, so I'm going to have 1,400,715. I'm going to take the antiderivative of this, which is going to give me 2x squared minus x cubed over 3. This is going to be from 0 to 4. Okay, and this is just going to give me 156,916 newtons. Okay. All right, so it is a very lengthy problem. There's a lot of things that you have to do, but this is basically the gist of what you're going to be doing.